Alright, so in this video, we will be diving into one of the most important skills in chemistry, and that's going to be writing electron configurations. So electron configurations basically tell us how the electrons are arranged in the atom. So what energy levels, sublevels, and orbitals that they occupy. And this is important because electrons fill up the orbitals of an atom in a specific order, starting from the lowest energy and then working their way up. So before we get into actually finding the electron configuration for an element, working through an example, just a couple things we should mention. So we know that atoms have different energy levels, and each of these energy levels will then have certain sublevels. So the first energy level actually only has one, the 1s sublevel. The second one will have the 2s and the 2p. The third will have the 3s, 3p, and 3d. The fourth will have 4s, 4p, 4d, and 4f. And there are more after the fourth, but we won't really be needing to look at that for this introduction. But basically, each of these orbitals, or each of these sublevels, can hold a certain number of electrons. For instance, the s orbital can hold up to only a maximum of 2 electrons. The p orbital can hold a maximum of 6 electrons. The d orbital can hold a maximum of 10 electrons, and the f orbital can hold a maximum of 14 electrons. So now that we've got this in mind, let's see how we can approach finding the electron configuration for an element. One thing to keep in mind is before we do this, again, it's handy to have the periodic table here, but we can see, let's say we want to find the electron configuration of oxygen right here. And so we need to first start by figuring out how many electrons oxygen has. And obviously that's important. If you want to find the electron configuration, we need to know how many electrons the atom has. And so this is going to be a neutral oxygen atom that we're finding the electron configuration for. We'll explain how we find the electron configuration for ions a bit later in the video. But looking at our atomic number, which is 8 for oxygen, we know that a stable or a neutral oxygen atom will have 8 electrons. So let's keep that in mind. We then can use this sort of pyramid-like schematic that we've created with the different sublevels to actually assist us in figuring out the order in which these different orbitals are filled up. So we can do this first by saying, all right, we draw a diagonal arrow down the schematic this way. So we start with the 1s. And if we remember, we see that the s orbital can only hold 2 electrons, so we fill it up to 1s2. We then go down again diagonally. So we now see we go to the 2s and fill the 2s2. So there's going to be 2 electrons in the 2s orbital. Next, we would go down diagonally to 2p and then the 3s. So we would start with 2p4 and stop there. Despite the fact that the p orbital can hold 6 electrons, here we only have 4 electrons in the p orbital. And the reason is it goes back to the number of electrons that oxygen even has, right? Oxygen here has 8 electrons. And what these superscripts, these exponent numbers, are basically denoting is the number of electrons in the orbitals. And so we can see that we have 2 plus 2 plus 4. Or 8 electrons. And so if there are no more electrons that this atom has in order to even continue to fill it up to 6 for this p orbital. And so this here would then be our final electron configuration. The electron configuration for oxygen is 1s2, 2s2, 2, excuse me, this is supposed to be if p, 2p4. All right, let's look at another example. Let's say we want to find the electron configuration of, silicon. Let's do that. So silicon, we see, has an atomic number of 14, and so it's going to have 14 electrons. So let's start by first drawing out that schematic, or that diagram, right? 1s, 2s, 2p, 3s, 3p, 3d. We can continue, but in this case, we wouldn't really need the fourth energy level. So let's start again with our diagonal going through the 1s. So we start by filling up the 1s2, filling up the 1s orbital to 1s2. So this sublevel is completely filled. We move on to 2s. So that would be 2s2 again, keeping in mind how many electrons we have so far. So far, we've only used up 4. Then to 2p and 3s. So we can fill up 2p6. This gives us 10, and then it brings us to 3s. So that is 3s2. We can completely fill up this sublevel as well. So since we now only still have 12 and we need 14, we then go down here to 3p. So we kind of follow this diagonal this way, which brings us to the 3p orbital next. And we only add 2 electrons to this 3p sublevel because, again, we only have 14 electrons to distribute throughout these orbitals. And so now we have 2 plus 2 plus 6 plus 2 plus 2, which is 14. And so this is going to be our final electron configuration for silicon. 1s2, 2s2, 2p6, 3s2, 3p2. And you'll also notice that this is very easy to find if we have a periodic table as well, without having to do this sort of schematic, although it does help with later instances, but we can actually just use our periodic table to help us out itself. And this is because we can see that this here would just be our energy levels going down in this fashion. And so we have our 1s2 filled up here. This would be 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s2, 3p, 1, 2. So just following this, we can see 1s2, 2s2, 2p6, 3s2, and 3p1, 2, and that brings us to silicon. And so we can use our periodic table in order to find the different electron configurations. So let's say we wanted to find chlorine. We don't have to really do much. We already know that we can see that all of this is going to remain the same. 1s2, 2s2, 2p6, 3s2, and simply 3p1, 2, 3, 4, 5. So if we wanted to find chlorine, we simply would have to change this number from a 2 to a 5. And that would be the electron configuration for chlorine. All right. So now let's look at something that may be a bit confusing, which is going to be our transition metals. Let's say we want to find the electron configuration for iron here. Let's say we want to find the electron configuration for iron. Well, let's start with our, schematic. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And so, let's see, it's kind of glitching out for a minute. All right. 4f. All right, sorry. Okay, so we have our schematic here. So let's start. So we can see that iron has 26 electrons. 26 electrons. So let's keep that in mind. Now we can follow 1s2, 2s2. Here, let me just draw this a bit lower. That is 1s2, 2s2, 2p6, 3s2, then 3p and 4s, you'll see. We'll fill up our 3p sublevel, 3p6, bringing us to 4s, which we would also fill up completely, 4s2. So you'll see that brings us down here, this 4s2. And now, according to our schematic, you'll see that we then go on to 3D before we go to 4P. So we have to fill out our 3P, 4S, and then 3D before we go down to 4P. So, see, this is a bit confusing here. Let me just write it a bit more neatly. That is 3P6, 4s2, and now 3d, that is 1, 2, 3, 4, 5, 6, 3d6. And so this then is going to be the electron configuration. And so I'm only mentioning this because it is for our transition metals like this, we would have to go to our d orbital before we go on to the p orbital here. And so for iron, in this case, that leads us to getting this electron configuration. So hopefully that makes sense. And that's again why this this schematic is helpful. Before we got to our d orbitals here, it was pretty straightforward. There wasn't necessarily a need for a schematic as we were just following the 2s, 2p, 3s, 3p, 4s. But we noticed that students often just fill up the 4p orbital, but according to our schematic, which just helps us see the order, we know that we have to fill up the 3d before we can move on to the 4p. So just keep that in mind. All right. Now let's see how we can find the electron configuration for ions. This is very similar to what we were doing so far, except we just have to keep in mind the number of electrons that we're dealing with. Let's say we want to find the electron configuration for the sodium ion. Let's start by figuring out how many electrons it has. We cannot, when we're dealing with ions, simply use this atomic number of 11. Sodium ion, the Na plus ion, does not have 11 electrons. Rather, if you'll remember, a positive charge means a lack of electrons because electrons carry a negative charge. So if we lose a negative charge, that is effectively the same thing as gaining a positive charge. Similarly, if an ion, let's say Cl minus, has a negative charge, that is due to gaining electrons, and so we gain a negative charge. So in the case of the sodium ion, we have a +1 charge because it has one less electron than the neutral atom of sodium would have. And so rather than having 11 electrons, we would have 11 minus 1, or 10 electrons. This is going to be the number of electrons that we have to use to write the electron configuration. Now, the rest of the steps will be exactly the same. We simply got 1s2, 2s2, right? 1s2, 2s2. We can move on to the 2p, 2p6, and well, we don't actually move down here as we would normally. I was going to demonstrate. You may think that we would go down here and just do a 3s1, and this would be incorrect because this is the electron configuration for sodium, not the sodium ion. The sodium ion, as you remember, has 10 electrons. This here accounts for 2 plus 2 plus 6 plus 1, that is 11. And so the electron configuration for our ion will then just be 1s2, 2s2, 2p6. This is the electron configuration for our sodium ion. Feel free to use your periodic table, come up with more examples like this for yourself, just to get the hang of finding these electron configurations. You'll notice oftentimes they are very similar. You'll just notice patterns forming, as a lot of it just remains the same. For instance, if we were all the way down here looking at selenium, all of these would be the same as compared to, say, silicon. Up until we reach silicon, the rest of this, would be new for our selenium, but otherwise the rest of this, all the 13 electrons prior to our reaching what we would have with silicon, would be exactly the same. And that actually brings us to the idea of the noble gas configuration, which we'll look at in another video, which is sort of a simplified version of the electron configuration so that it's less tedious to write it out. But we'll look at that in another video. Let's look at another example for writing the electron configuration for an ion now, though. Let's say we want to find the electron configuration for the sulfide ion, that is S2 minus. Well, normally, sulfur has 16 electrons. But here we can see that this ion has a -2 charge. And so that means that it has 2 more electrons than the neutral atom would have. And so our total number of electrons here would actually be 16 plus 2 giving us 18 electrons. And it's important that you realize, again, that the negative charge means you have more electrons and the positive charge means you have lost electrons. That's often a common source of error, getting that mixed up. So just keep in mind, remember that electrons have negative charge, and so gaining more electrons would lead to a negative charge for the ion, and losing of that negative charge would effectively lead to a positive charge for, your cations. Well, we can now start by, let's just see if we can find the electron configuration of our neutral atom first. Sulfur, we can use 1s2, 2s2. Again, I've stopped using that schematic for now as I'm comfortable with the way these orbitals are filling up. If you still want to use them, obviously feel free to draw out the schematic and draw the arrows to help you find your way. So that's 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4. And this gives us 2 plus 2 plus 6, which is 10, plus 2, 12, plus 4, 16. But you'll remember that this is a sulfide ion that we're trying to find the electron configuration for. And that means we have 18 electrons, right? And so this is not the electron configuration that we're going to be, looking for. Rather, it would be 3p6. So this is the electron configuration of our sulfide ion. All right, that brings us to the end of this video. This is just a basic introduction to electron configuration. I will be making more videos with some of the exceptions, more complex examples, looking at transition metals, higher orbitals, higher energy levels, and so on, as well as the noble gas configuration, so keep a lookout for those. But in the meantime, if you did enjoy this video and found it to be helpful, please show your support by liking and subscribing, and leave in the comments what you'd like to see next, and I'll see you in the next one.